So this video is also part of the CC11 topic, so it only comes up on paper 1, and we're going to look at the extraction of metals. So in the two previous videos that we've looked at in this topic, we've seen that metals are reactive. And because they're reactive, they will react with the elements around them and form compounds. So what this means is that even though metals occur naturally, so all of the elements on the periodic table, they are naturally occurring, they're not made in a lab. Although they do occur naturally, you're not going to find them as pure elements because they will react with other elements around them and form compounds. So for example, you're not going to find pure sodium, it's going to react with the oxygen in the air, it's going to react with water vapor in the air, and it's going to form compounds. These compounds are typically found in rocks, and these rocks are called ores. And what we're going to look at in this topic is how to extract the metal from the compound. So you'd have to get that compound out of the rock and then extract the metal from the compound. So extraction, the process of obtaining the pure metal from the compound. So for example, if your compound was iron oxide, because iron had reacted with the oxygen around it, then you would want to extract the pure iron from the iron oxide. There are two main methods of extraction. There is electrolysis, which we looked at in CC10, and then there's also just chemical reactions with carbon. And these are actually displacement reactions, which we've seen on the previous two videos. So for example, if I took carbon and zinc oxide, we said when we looked at the reactivity series that carbon was included in the reactivity series even though it was not a metal. And now we're going to see why. So if I just show you again that reactivity series, I've highlighted carbon here in orange, and you can see it's kind of midway in your reactivity series. It's less reactive than the metals above it, but it's more reactive than zinc, iron, copper, silver, and gold. Again, I've highlighted hydrogen in orange because it's also a non-metal. But you've got zinc, iron, copper, silver, and gold that are all less reactive than carbon. And our rule with displacement reactions was always that, if the element that's by itself is more reactive than your metal in the compound, then they can swap places. So I've got carbon and I've got zinc. And carbon is more reactive than zinc, so they are going to swap places. You're going to end up with the zinc by itself, and the carbon is going to react with the oxygen. Now you'll get the mark for writing carbon oxide, but typically when carbon reacts with oxygen, you get carbon dioxide. In this reaction, you're starting off with carbon, you're reacting it with zinc oxide, and you're ending up with pure zinc. So this is your metal compound. Zinc is your metal, it reacted with oxygen, it formed zinc oxide. By reacting zinc oxide with carbon, you are obtaining pure zinc. You're removing all of that oxygen from zinc and ending up with the pure metal. So you're using carbon to extract zinc from zinc oxide. This same reaction will also work if you react carbon with copper oxide. Carbon, again, if you look at your reactivity series, is more reactive than copper. So if I react carbon with copper oxide, I'm going to get pure copper. And I'll get carbon dioxide. So I'm removing the copper from the copper oxide. I'm being left with pure copper. However, this is only going to work on the metals less reactive than carbon. So if I look at the following example, carbon plus aluminium oxide, using my reactivity series, I can see that aluminium is more reactive than carbon. Therefore, carbon cannot take its place. So carbon and aluminium will not swap places. I'm not going to get a reaction. So I can use carbon to extract zinc and copper and iron, but I can't use carbon to extract any metal more reactive than it, including aluminium. Now you might think to yourself, okay, fine, maybe you can't use carbon, but there are plenty of metals more reactive than aluminium. What if I reacted aluminium oxide with magnesium or with calcium? Could I use that to obtain pure aluminium? And if we look at the reaction below, I've written out such an example. So I've got magnesium and I've got aluminium oxide. Now magnesium is more reactive than aluminium. So they will swap places, and when they do, you do obtain pure aluminium and you end up with magnesium oxide. So I can use magnesium to obtain aluminium from aluminium oxide. However, the problem with this is that if you were doing this on a large scale, and I had to use magnesium or one of these metals above aluminium. If I was doing this on a large scale, this would be expensive. Okay, these metals, you would need to have them in their pure form, which would be expensive. They're also very reactive metals, so it wouldn't be safe to store large amounts of potassium or sodium to use them to extract aluminium from aluminium oxide. So it's just not feasible to use these really reactive metals to extract other metals. That is why for all the metals above carbon, we use electrolysis instead. So that I'm not going to go into electrolysis, we did it in CC10, but you use electrolysis for all metals above carbon, and then for the metals below carbon, you use carbon. Now, could you use electrolysis for the metals below? Yes, but electrolysis is also expensive. So we prefer to use carbon. Carbon is just like you'd use coal, and it's cheap and it's safe, and it's much easier than electrolysis. So where you can use carbon, you do. For the metals more reactive than carbon, you're going to use electrolysis instead. And that's summarized here. Sorry. It's summarized here in this table. Method of extraction. So I've got carbon here. All the metals more reactive than carbon, I use electrolysis. The metals less reactive than carbon, I heat them with carbon. You've got some metals here at the very bottom, silver and gold. They are actually so unreactive that you can find them as pure metals. They're so unreactive that they don't react with the elements around them. You don't need to extract them at all. You'll just find them as pure elements. There's one more tiny little thing we have to cover on this topic, and that's oxidation and reduction. So we came across oxidation and reduction in the last topic, and we said oxidation was loss of electrons and reduction is gain. But there's another definition for oxidation and reduction. You can also define oxidation as being the gain of oxygen. So yes, it's the loss of electrons, but you can also define it as being the gain of oxygen. And reduction, which was the gain of electrons, can also be defined as being the loss of oxygen. And in these reactions that I've gone through above, you can be asked what is oxidized and what is reduced. Rather than working out what's losing and gaining electrons like we did in the last video, it's much, much easier because we can just look at what's gaining oxygen and what's losing oxygen rather than figuring it out with electrons. So if I come back up here to my carbon zinc oxide, if I look at my equation, I need to look at what I've got on the left-hand side and ask myself what doesn't have oxygen on the left that does have oxygen on the right. So if I look here at carbon, on the left-hand side, it's just carbon by itself, but on the right-hand side, I've got carbon dioxide. So over the course of this reaction, carbon is going from carbon to carbon dioxide. Therefore, I can say that carbon is gaining oxygen. I can say that carbon is oxidized. Okay? If I look at the next equation, I'll see that that's the same again. Carbon goes from being carbon to being carbon dioxide. In the next equation, carbon is once again oxidized. And carbon is always going to be oxidized in these equations. It starts off as carbon, it ends up as carbon dioxide, it's gaining oxygen, it's oxidized. The opposite of oxidation is reduction. Reduction is the removal of oxygen, so I need to look at what has oxygen on the left that doesn't have oxygen on the right. So if I look back at my first equation, I've got zinc oxide going to just zinc. So zinc has got oxygen on the left, it's zinc oxide, but on the right, it's just zinc. That means that zinc is being reduced. And I don't write zinc oxide is reduced, I write zinc is reduced. It's zinc that has oxygen and it's then losing it. So zinc that's being reduced. If I look at the next one, copper oxide becomes copper. Copper had oxygen on the left. It doesn't have oxygen on the right. So again, copper, not copper oxide, copper is being reduced. So it's far easier than doing the half equations that we did in the last video. You're just looking at what gains oxygen. It's going to be carbon, that's oxidized. What's losing oxygen? And it's the metal that is being reduced. So this method is actually called reduction with carbon because the metal gets reduced when you react it with carbon. So reduction with carbon, you react the metal with carbon and you lose oxygen. So I'm going to get you to press pause and do a few questions for me. I want you to start here on question 5. Why do some metals not need to be extracted? And do them right down as far as question 15. So press pause, have a go at these questions, press play when you're ready to see the answers from question 5 down as far as question 15. Okay, so I've been a little bit lazy. I haven't written the answers. I'm just going to call them out. So question 5, why do some metals not need to be extracted? Some metals are found as pure metals. Okay, so some metals are pure. The reason they're pure is because they're so unreactive that they don't combine with other elements, and your examples will be silver and gold. But if you just write some metals are found as pure metals because they're unreactive, that will get you your mark. In question 6, a method. So the methods we looked at are electrolysis and reduction with carbon. The one that you're going to use will be determined by the position on the reactivity series. So iron is less reactive than carbon, so I can use carbon. Aluminium is more reactive than carbon, so I need to use electrolysis. Sodium is more reactive than carbon, so I have to use electrolysis. Zinc, less reactive than carbon, I can use carbon. So it's all just determined on the position in the reactivity series. More reactive than carbon, you use electrolysis. Less reactive, you're using carbon. And it's the metal that you're looking at. Complete the word equations. This one I have written out. So carbon is more reactive than copper. They swap places. You get copper and carbon dioxide. The next one you get iron and carbon dioxide. Then you get zinc and carbon dioxide. And it doesn't matter which way around you write this. You can write carbon dioxide plus copper instead. It's still going to be correct. If calcium oxide was heated with carbon, no reaction would occur. Explain why. You can say that carbon is less reactive than calcium, or calcium is more reactive than carbon. That's going to be your first mark. And your second mark is going to be carbon cannot displace calcium. So carbon's not able to take calcium's place. Carbon cannot displace calcium. If you cannot use carbon, then what are you going to use? You're going to use electrolysis. Okay, it's more reactive than carbon. You're going to use electrolysis. What's oxidation in terms of electrons? It's the loss of electrons, but in terms of oxygen, it's the gain of oxygen. So loss of electrons, gain of oxygen. Reduction is gain of electrons, loss of oxygen. Identify what is being oxidized. So in each case, carbon is being oxidized. It's going from carbon to carbon dioxide. In every equation, carbon is gaining oxygen. Carbon is oxidized. For the reduction, it's always the metal. So it's copper being reduced in the first equation, iron being reduced in the second, and zinc being reduced in the third. It's not copper oxide that's being reduced, it's copper. So it's just the name of the metal. It's the metal that's losing oxygen. What are redox reactions? They are reactions in which oxidation and reduction take place. And that's all you would need to say there.